This is also getting interesting now for people who already know about the basics of contrasts. I think this is not as widely appreciated yet. So the hypothesis matrix and the generalized inverse. So I will talk about linear models again. We're still in the linear model family. And I will ask the question, how can we create a contrast matrix? So not just use a contrast matrix that seems to maybe fit, or that maybe doesn't, and how can we create one? And in my examples, I will actually use, again, the example with 4 factor levels that we had before. And I will now show how we can create the contrast matrices that we discussed in the previous session, how we can create them ourselves by specifying the hypotheses. So now this is kind of you could say a pointless endeavor, because now we are creating the contrast matrices that we already have and know what they test. But this is just to illustrate that you can use this procedure to create the contrast matrices that we already know. But that means we can also create other new hypotheses, contrast matrices that test other hypotheses. Then I will talk briefly about centering and about non-orthogonal contrast and about effect size statistic for contrasts. Yeah, that's the overview of the session. So the question is how to derive custom contrast matrices from hypotheses. And we have defined a 4-step procedure to do that. The first step is to define the hypothesis. So you have to be really clear about what your hypotheses are that you want to test. Then we can extract the weights and write down the so-called hypothesis matrix. And then we can convert the hypothesis matrix to a contrast matrix using this generalized inverse operation. And then if we have the contrast, we can assign the contrast to a factor and run the linear model. And this procedure of 4 steps is explained in detail in this paper that I wrote with some colleagues. Yeah, where we explain how this generalized inverse conversion, like this whole procedure is basically explained there, and then different examples and applications. So if you want to read it up, I'd advise you to look at that. Okay, we will again use the same, as I said, the same contrast that I talked about before. Some contrast treatments, some Helmut and repeated or sliding difference contrast. But now I will create these contrast matrices starting from the hypotheses. Start with the treatment contrast. First step, define the hypotheses. So what are the null hypotheses that are tested in the treatment contrast? The first null hypothesis states that the mean of x1, so mu1, now I use mu1 to indicate the mean of condition x1, is equal to 0. So that's the intercept in the treatment contrast, that x1, the mean of x1 is 0. The null hypothesis in the second null hypothesis is that the mean of x2, so mu2, is equal to the baseline mu1. And then the mean of x3, so mu3, is also equal to mu1. And the fourth hypothesis is that the last mean, mu4, or mean of x4, is equal to the mean of x1. Okay, so first we compare the first condition mean to 0, and then we compare all other condition means to the first condition mean. So now we can reformulate these hypotheses slightly. So we will put 0 on one side of the equation in all of these cases, and I will write it up in a way that all the condition means, mu1 to mu4, are all represented. So for the first null hypothesis, this is simply 1 times mu1 plus 0 times mu2 plus 0 times mu3 plus 0 times mu4 equals 0. This is just the same hypothesis, just written slightly differently. In this case here, I subtract minus mu1 from both sides. So on the right-hand side, I end up with a 0. On the left-hand side, it's minus mu1 plus mu2. And again, I write it up here with the coefficients minus 1 times mu1 plus 1 mu2, and mu3 and mu4 are not in the equation, so they get a 0. Okay, so you can see that I write these weights here. So this is there's a weight of 1 for the mu1, and here we get a weight of -1 for mu1 and +1 for mu2. So we are comparing mu2 versus mu1. How about the third hypothesis? Again, I subtract mu1 on both sides, so I get minus mu1 plus mu3 equals 0. And now I have minus mu1 plus mu3, and mu2 and then mu4 are again cancelled out. They get a 0, and all of this should be 0. So these are just different ways of writing these same hypotheses in a different way. So how about the last hypothesis? Just as before, minus mu1. So we have minus mu1 here. Mu1 is always subtracted. And now mu2 and mu3 don't play a role, get a 0, and we get 1 times mu4 equals to 0. So is that clear? If there are any questions about that, let me know, because that's we will do that now over and over again. So it's good to clarify this right now, if there are questions. So if I have written this down, these hypotheses, in this way, what I can do, I can easily extract the weights. This here, +1, -1, -1, -1, 0, 1, 0, 0, and so forth. So I extract them here. So I first look at the first hypothesis, B1. So x1 is 1, and the other ones are all 0, 0, 0, 0. Then the second hypothesis, -1, +1, 0, 0. Okay, -1, +1, 0, 0. And then the first one always gets a -1. Here the +1 is in the third location, and here the +1 is in the fourth location. So now I've just extracted the weights from these hypotheses and written them. That's what we call a hypothesis matrix. So this is a very dense or very dense form to write down these hypotheses about the condition means and how to compare them with each other. And note that I use here the command rbind. So in the hypothesis matrix, each hypothesis is 1 row. However, mathematically. However, to simplify comparison with the contrast matrix, I use this function t, and this just flips rows and columns such that each hypothesis now has 1 column, like in the contrast matrix. And again, on the different rows are defined by the different condition means. So this is the output of this command that you can see here, and you can easily read this hypothesis matrix and read what the hypotheses are that I implement here. The first hypothesis is that x1 is 0. There's just a 1 here. All other conditions are ignored. The hypothesis 2 here, called B2, is the difference between x2 and x1. You can see here +1, -1. The third hypothesis is x3 against x1, and the last hypothesis is x4 against x1. So this is an easy way to read the hypotheses out of this matrix. And the nice thing about this hypothesis matrix, if you write this down, you can perform a mathematical operation that is called the generalized matrix inverse. And I will not go into the detail of what that means in specifically, but we just take it for granted that if we apply this generalized matrix inverse operation, and I define a function for how to do that. So in the mass package, there's this function G inverse, but that doesn't convert the column names and row names. It doesn't conserve the row names and column names. So I create this little function that does the generalized inverse operation while preserving row and column names. So if I apply this generalized inverse to the hypothesis matrix, what we get is the contrast matrix. Now we can look at this contrast matrix. This is the contrast matrix that implements these hypotheses that we have specified above. If I look at that, I get a column of 1s. Okay, there's an intercept. We can recognize that. So the first hypothesis is that is an intercept term here. And the first contrast is an intercept term. And then the second contrast here. Then we can see if we can look at, when we look at this matrix, it looks exactly like the treatment contrast. Here for comparison, I add the treatment contrast and I add an intercept to the treatment contrast. And we can see that this matrix down here looks exactly the same as this matrix. So magically, or not magically, but nicely, by writing down these hypotheses, writing them in a way that we can extract the weights And then applying this generalized matrix inverse, we get the contrast matrix for the treatment contrast. And that's exactly what we started out with, right? We said, what are the hypotheses of the treatment contrast? We always compare everything to the baseline and the baseline to 0. So we can also assign this new contrast matrix that we observed to the contrast attribute of the factor. And of course, we get out the same estimates. So intercept of 10, first difference is 10, 0, and 30. So this works, but we can already see this at this stage that the contrast matrix comes out as the treatment contrast matrix. So this is pretty nice, right? We can now define arbitrary hypotheses, write them down that we can extract these weights, write them in the hypothesis matrix, and then we should simply apply this generalized matrix inverse and we get the contrast matrix that we need. Even if sometimes the contrast matrices are very unintuitive. So sometimes there are cases where you can specify the contrast matrix directly, but sometimes they are really not so clear. And then if they are not so clear, we can just work with the hypotheses. Okay, there's one nice point about these contrast matrices, about this generalized inverse. It allows to flip back and forth between hypothesis and contrast matrices. So applying the generalized inverse to the contrast matrix yields the hypothesis matrix. So this is the hypothesis matrix for the treatment contrast. The first condition is compared to 0, the second to the first, the third to the first, and the fourth to the first. And now we apply this generalized inverse matrix twice, generalized matrix inverse twice. And what do we get? We get again the same hypothesis matrix. Can compare these matrices are exactly the same. Now, if I apply the generalized matrix inverse to the contrast matrix? So XTR is the contrast matrix for the treatment contrast, and we see that we again get the same thing. And this can be nice if you are confronted with a situation where some authors, for example, or someone has defined some contrast matrix, and you are not sure what hypotheses it tests. So what you can do, you can simply apply the generalized matrix inverse, and you get the hypothesis. It shows you the hypothesis matrix that you can read out and see what hypotheses are tested by this contrast matrix. There's one important point. For the treatment contrast, it's crucial to include the intercept in the inversion. So if you have a contrast matrix here, XTR, that is simply the treatment contrast, including the intercept, and you apply the generalized inverse, then you get this hypothesis matrix that I showed you before. The first term, the intercept tests the mean of x1, and then always the other means are compared to x1. But if you, in the contrast matrix, leave out the intercept, so here it's the same as above, just not an intercept term included, and then you perform the generalized matrix inverse, you get a hypothesis matrix that looks very different, right? If you don't have an intercept, actually, then the first contrast estimates the mean of x2, the third the mean of x3, and the last the mean of x4. This is not something we want to investigate. So this is weird. So for the treatment contrast, we really need the intercept term when we do these generalized matrix inverse transformations. Okay, so how does it look for the sum contrast? For the sum contrast, we said the intercept captures the grand mean, and then each coefficient tests the difference of one factor level against the grand mean. So we will look at the first hypothesis here. So the grand mean can be computed as mu1 plus mu2 plus mu3 plus mu4 divided by 4. That's just the grand mean. And now this grand mean, by the null hypothesis, mu1, so the mean of x1, should be the same as that grand mean. So mu1 equals that grand mean. And the second hypothesis is that mu2 equals that grand mean. And the third hypothesis is that the mu3 equals that that grand mean. Okay, these are the hypotheses in the sum contrast. Now, how can we transform this into a format that we can extract the weights? So first, we can subtract the grand mean on both sides in each of these equations. So then we get mu1 minus the grand mean equals 0. And how can we get now into this format on the right? We can see that mu1, there's 1 mu1 minus 1/4 mu1. Okay, that's 3/4 mu1. 1 minus 1/4 is 3/4 mu1. And for all the other numbers, mu2, mu3, mu4, there's always 1/4 minus 1/4. So minus 1/4 mu2, minus 1/4 mu3, and minus 1/4 mu4. Okay. And now we have this representation again that we want. It looks a bit unusual, but it's directly coming from this hypothesis that we have specified up here. How about the second hypothesis? Mu2 equals the grand mean. So we just say mu2 minus the grand mean equals 0. And now mu1 is only 1 minus 1/4 mu1. And now mu2 is 3/4 because it's 4/4. So 1 times mu1 minus 1/4 mu2. Sorry. 1 times mu2 minus 1/4 mu2 is 3/4 mu2, and the other ones are minus 1/4. And the same applies to mu3. So we have now 3/4 mu3, but the other mu's are all associated with minus 1/4. Okay, so this took a bit of work, but when we start out with the hypothesis, this is directly translatable into this representation. And now we can again extract the weights, write them into this matrix, and we can see here. So from this hypothesis matrix, you have to do a bit of math to see where the hypotheses come from. But you see here, there's first 3/3, 3/4, and then always minus 1/4. And the 3/4 is first in x1, then x2, and then x3. So this is how this matrix looks like. Okay, so what happens if we apply the generalized matrix inverse? It looks exactly as the sum contrast. So we have seen the sum contrast here. There's a -1 for the last row, and then there's a diagonal of 1s with everything else being equal. And this is also what this hypothesis matrix looks like. This contrast matrix derived from the hypothesis matrix looks like. So here we have a row of minus ones, and then the ones on the diagonal. So again, we can assign that to the model, and the numbers turn out fine. But this is clear already from the contrast matrix because it's exactly the same. We obtain this contrast matrix just by looking at the hypotheses from that we think should be encoded in the sum contrast. Okay. This was just another example how this works. Let's do it one more time for the Helmut contrast. As I said before, the Helmut contrast, the standard Helmut contrast, if we look at the standard Helmut contrast, it didn't quite capture the differences that we intended it to capture, right? The contrast matrix looks like that. If we take the generalized inverse of the contrast matrix of the Helmut contrast, we get the hypothesis matrix that this Helmut contrast tests. And we can see here that it's not, the first coefficient doesn't test the difference between the first two conditions, but it captures half the difference. So 1/2 minus and minus 1/2, not 1 and minus 1, but this is divided by 2. And here in the next column, it's divided by 3 actually, and then it's divided by 4. So we can clearly see in the hypothesis matrix that the Helmut contrast, the standard Helmut contrast, doesn't test these differences that we expect them to test, but they test these scaled versions of the Helmut of the differences. Okay, we've seen that. So how can we define our own Helmut contrast that tests the hypothesis that we want it to test? So the first hypothesis in the Helmut contrast, that's what we said, should test the difference between the first and the second factor level. And we can encode this here in this way that we have minus mu1 plus 1 times mu2, and mu3 and mu4 are not part of the equation, so they are associated with the 0. Then the second hypothesis. We say the second hypothesis is that the average of mu1 and mu2 is subtracted from is subtracted from mu3, and the difference is 0. So how do we translate that? Minus 1/2 mu2 minus 1/2 minus 1/2 mu1 minus 1/2 mu2, sorry, plus 1 mu3, and that should be 0. And the last hypothesis is that this fourth condition mean mu4 is equal to the average of the first three. So we have minus 1/3, minus 1/3, minus 1/3, and a 1 back here. So we extract the condition, we extract the weights, and we can see now this looks much more reasonable. This is the hypothesis matrix that we expect, right? The second condition is compared to the first, then the third is compared to the average of the first two. So the minus 1/2 and minus 1/2 indicates that there's an averaging between these two. And the last one shows the last condition against the average of the first three, because it's three conditions we need to do. You need to compute 1/3 each time. So if we convert the hypothesis matrix to the contrast matrix using the generalized matrix inverse, we see that the contrast matrix now looks much less nicely and cleanly than the contrast matrix by the Helmholtz function. Right here we have 1 and -1, 2 and -1, 3 and -1. But now with this new matrix, it's 1/2 and minus 1/2, 2/3 and minus 1/3, 3/4 and minus 1/4. So this doesn't look as nice anymore. And probably, I assume that the people who have come up with the Helmholtz contrast have decided that it's important to have a nice contrast matrix. But I think it's much more important to have a nice way to represent the hypotheses. So this is not the usual way how people look at this, but the hypotheses and the differences that we test are of course much more important rather than what the contrast matrix itself looks like. So if we use this contrast matrix from the Helmholtz contrast, our custom designed Helmholtz contrast, so this is called X Helmholtz, the contrast matrix for Helmholtz, we can assign that to our factor. And if we look at the comparisons that are at the estimates of the model now, we can see that the intercept is the grand mean. Okay, that's not new. The first contrast should be 10. The difference between x2 minus x1, 20 minus 10 is 10. So that's what we see here. It's a 10. The second contrast should be -5, exactly what is estimated by the model. And the last difference should be 26.667. And again, this is exactly captured. So you see that by this manual encoding of the hypotheses into defining the weights and extracting the weights and doing the transformation via the generalized inverse, we get a contrast matrix of the Helmholtz contrast that is actually better than the standard Helmholtz contrast, because it estimates exactly the differences that we want to estimate, and we don't have to multiply by 2, 3, 4, and so forth to get. So it's not capturing the scaled estimates anymore. To remind you, the Helmholtz contrast, if you use the standard Helmholtz contrast, then you get 5 minus 1.66 and 6.66 instead of these numbers. So we see already in this case where we have a standard Helmholtz contrast, defining these hypotheses is already much better than just using the standard. Okay, and now you might argue, well, it might be nicer, but it's already also quite a bit of work to write down these hypotheses, extract the weights, how to calculate that exactly. I will show you that we have a R package that does that work for you. So you only have to implement, only have to write down the hypotheses, and the R package does the rest. But before we get to that, I want to discuss the repeated and sliding difference contrast. How does it work for these? So we define our hypotheses. So the difference in the hypotheses in repeated contrast is that you always compare neighboring factor levels. So mu1 is compared to mu2, mu2 to mu3, mu3 to mu4. If we write this down, we always have this -1 for mu2 and +1 for mu2, -1 for mu1 and +1 for mu2, and then 0, 0. Then here -1 for mu2 and +1 for mu3, and mu1 and mu4 are 0. And then the first two are 0, and mu3 gets a -1 and mu4 gets a +1. So if we look at the hypothesis matrix, we can see that x2 is compared to x1 in the first factor, in the first hypothesis. The second hypothesis is that x3 is compared to x2, so +1, -1, and then we can see that in the third hypothesis, x4 is compared to x3. So this is very straightforward, right? You can easily read out the hypotheses that are tested by this matrix. And now you perform the generalized matrix inverse to get the contrast matrix. And interestingly, it turns out that this is exactly this contrast matrix from the sliding difference contrast that we saw earlier. So when we obtain this sliding difference contrast, we see that this exactly looks like that. We said before that this is very unintuitive. We don't know exactly how to obtain this contrast matrix. But here we see that it directly follows from this very easy implementation of the hypothesis in the hypothesis matrix. Of course, we can again assign that to the model and get the correct differences that we would expect. Let us try out one thing that is new. So we already saw that the Helmut contrast was a bit different than the standard, but so let us try out a treatment contrast with the baseline, where the baseline is the grand mean. So why would that be interesting? So far we haven't really discussed cases where that is interesting, but I can tell you that when we have more than one factor in our design, for example, if we have 2 or more factors, then it can be very important what the baseline level is. And then we usually want the baseline to capture the grand mean instead of the baseline level of one factor level. It's also important when we talk about linear mixed effect models, when we talk about random effects. The random effects also depend on the contrast coding. And also in that case, we generally want that the intercept measures the grand mean. That's actually the better thing. But now, what if we have a treatment a situation where we have 3 treatments and we want to compare them to a baseline control condition, but we also want to have the grand mean. So let's try to write down the hypotheses that we want to have. We want to have the grand mean, so mu1 plus mu2 plus mu3 plus mu4 divided by 4. That should be tested against 0. And then we want a treatment contrast where each level is compared to mu1, okay, to the baseline level. We can reformulate that again. So 1/4 for all the condition means in the intercept hypothesis. And then we have always -1 for the mu1, and then +1 for mu2, for mu3, and mu4. So this is what we did before. We can the other condition means don't play a role. So we can see that again the matrix here. So the first the intercept is always coded in each condition by 0.25, 1/4, because we average across all 4 conditions. And then the hypothesis shows that as in the treatment contrast, first the second level is compared to the first, then the third level is compared to the first, and the fourth level is compared to the baseline level. Okay, let's apply the generalized matrix inverse. And now this is the contrast matrix that we get. It looks kind of weird again, -1/4, 3/4, -1/4. So it's not directly transparent what this tests, but we know that it should test these hypotheses. So it should test the treatment contrast where the intercept is the grand mean. We see that the standard treatment contrast certainly looks different, right? As a reminder, this is how the standard treatment contrast looks like. And now this looks very different. But let's try and apply this new contrast matrix, X for treatment, the X matrix, or the contrast matrix for the treatment factor. And let's apply that to our contrast attribute. We take columns 2 to 4 because we remove the intercept. The intercept is added automatically. And then we run the linear model, and what happens? We can see that now the intercept is the grand mean. It's 20. So the mean across all conditions we said is 20. That's exactly what we want. So how about the estimates for the different coefficients? So the first one should be the difference here. That's 10. x2 versus x1. That's 10. How about the x3, the second slope? That's 0, as it should be. X3 is exactly the same as x1. And how about the last one, x4? That's exactly 30, as it should be. 40 minus 10 is the difference is 30. So we can see that by defining this new set of hypotheses, we obtain a contrast matrix that is not very transparent. The hypothesis matrix is clear. There we can see what's going on. The contrast matrix is kind of weird, but it tests exactly what we wanted to do. So we have now created a new kind of contrast that is maybe not considered in many standard analyses. Okay. Are there questions about this generalized matrix inverse aspect? We can discuss them now. Let's see, take a quick look here. Okay. Then let's go on with centering and non-orthogonal contrasts. Two important aspects of contrast are whether they are centered and whether they are orthogonal. So the centered contrast can be defined. So these are just some additional aspects about contrast that one should know. So centered contrasts are defined that the contrast weights or contrast coefficients that they add up to 0. So Ci is the contrast coefficients for I factor levels, capital I factor levels I. So what does it mean? So if you have the treatment contrast for each column, we can sum them up and see whether the sum of them is 0. So for the treatment contrast, surely the first column sums up to 1, the second also. We can compute that here by using call sums. So for each column there, the sum is computed, and we can see that it's 1 and 1. So here, clearly, it's not 0. That means treatment contrasts are not centered. Some contrasts, by contrast, we sum up the first column, 1, 0, minus 1 is exactly 0, right? And the second column is also 0. 0 plus 1 minus 1. We can do that computation here by call sums, and we see that the sum contrast is centered. Also, Helmholtz contrasts are centered, and simple difference contrasts, repeated contrasts are also centered. For centered contrasts, the mean of the contrast coefficients is 0, and therefore the intercept tests the average dependent variable across all conditions. So it tests the grand mean. For non-centered contrasts, it is crucial to include this. We have seen this before. It's crucial to include the intercept when doing the inverse operation. So when we have the treatment contrast and we do the generalized inverse matrix inverse with the intercept, we get this hypothesis matrix that shows that the first level is compared to 0, and then the second and third are compared to the first. But if we leave out, I think I showed this before, when we leave out the intercept, we get the strange hypothesis matrix. However, when we use some contrasts, that is, when we use a centered contrast, then we don't have to. Then the intercept doesn't matter. So if the contrast is centered, then we can ignore the intercept. We have actually already done this in all the examples that I showed you. So here's the sum contrast with an intercept, and we do the inverse, and we see this is the hypothesis matrix for the sum contrast. And now we leave out the intercept, so this is empty, and do the inverse operation. And if we ignore this first column that's coding the intercept, the hypothesis matrix looks exactly the same. That is, for centered contrasts, leaving out the intercept does not change the generalized inverse. That's important to know. But if you have a contrast that is not centered, like the treatment contrast, then it's very important to consider the intercept in the inverse operation. Then how about orthogonal contrasts? So orthogonal contrast states something about how two contrasts relate to each other. So if we have two contrasts, contrast 1 and contrast 2, and then we have different factor levels I. In our example, capital I was 4, so I varies from 1 to 4. If we multiply contrast coefficients across always 2 contrast coefficients and sum them up across all 4 factor levels, then this should be 0. Another way to compute to test whether contrasts are orthogonal is just by computing the correlation. So if we have the treatment contrast and you compute the correlation between them, then we get the following correlation matrix. So on the diagonal, we see ones. That's just the case in correlation matrices. But we see on the off diagonals here and here and here, we see minus 0.33. So that shows that the contrasts here are correlated. So they're not independent. They are not orthogonal. And that's a bit like, or they're not just a bit, and that's like in multiple regression analysis, where we have different predictors, and the different predictors are not orthogonal to each other, but they are correlated. So if there are very high correlations between the predicted terms, that can lead to problems in the estimation of the parameters. So that shouldn't be the case. If we look for the correlation matrix for the Helmut contrast, we can see that these off diagonals are 0. That means the Helmut contrasts are completely orthogonal to each other. They tap into independent sources of variance. The sum contrast, again, is not orthogonal. So they're correlated by 0.5 here. And also the sliding difference contrast is not orthogonal. Correlations up to 0.77. And you can easily imagine why this happens, because if two contrasts, so let's see, the first contrast compares 1 against 2, and the second contrast compares 3 against 2. So 2 enters both contrasts, right? If 2 is large, then this will affect both contrasts similarly, so they are not independent. Look, however, if you have what happens with the sum contrast if you have a 2x2 design? 2 main effects and an interaction. We will look at this later in more detail. Let's say these 4 conditions are a 2x2 design, and the first column codes factor A. So the first 2 conditions against the second 2 using sum contrast, and the second one codes factor 2, the first and the third against the second and the fourth, and then there's an interaction between them. Then actually the contrasts are orthogonal. In the end, one can say that orthogonal contrasts have statistical advantages, especially highly correlated contrasts can be very difficult to estimate. However, in the end, research hypotheses that we have are in their very nature often not orthogonal to each other. And therefore one should, so the questions that we have are often not orthogonal. And then one should guide contrast construction by the research hypotheses that one wants to study. So it doesn't make sense to test contrasts that we are not interested in, right? We have hypotheses and maybe they are not orthogonal to each other, then that's the case. But then we still should use a contrast that tests these hypotheses and not a different contrast that tests something else. So it's desirable to have orthogonal contrasts, and ideally you can create an experimental design where the hypotheses are orthogonal to each other. But if that's not the case, then and we can see here that many contrasts, also the standard contrasts, are correlated. So only the Helmut contrast in this example is orthogonal. Okay. Let's sum up. We have this matrix. I've introduced this matrix operation, the generalized matrix inverse, implemented in this function G inverse 2, and the hypothesis matrix, which we call HC. And we have I've introduced this 4-step procedure where you write down the hypotheses, and by following this procedure, we obtain the correct contrast matrix for the hypothesis that we actually want to study. So we can really care about the hypotheses that we want to study and don't have to care about how exactly the contrast matrix is designed, because this can often be very unintuitive, while the hypothesis should be clear to us. And an additional feature of this setup we learned is that if we have a given set of contrasts, we can determine which hypotheses these contrasts actually test. So if someone uses a very complex contrast matrix, we can test or we can look at the hypothesis matrix and see whether the contrast matrix actually tests the hypothesis that one wants it to test. And so one general piece of advice would be always test whether your contrast coding is correct. For that, you can simulate data using the mixed design function. The easiest way to just use a between subject approach. Create a figure of the condition means, run a linear model, simple linear model with the contrast coding, and check whether the regression coefficients match the figure. So this is always a good advice to see whether your procedure is working correctly before you enter real data in a linear mixed effect model where these checks cannot be done easily anymore. Okay. Yeah, this was the first part of this session. Again, to remind you the details of this generalized matrix inverse operation and how you get from a hypothesis matrix to a contrast matrix, I refer you to this paper if you want to have a closer look. Oh yeah, it's basically showing similar content, but you can read it up again if you want. So you could, and of course, you could argue that this procedure that I showed you is rather complex. You have to change. You have to start with the hypotheses, but then you have to write them in this hypothesis matrix format. So this can involve some transformation. So it's a bit inconvenient.